Shall we start or we should wait for 2 minutes?
Sir, we wait for 2 minutes.
Okay, okay,
Okay.
ma'am.
But we
Okay.
can ask Dr. Samrith to share his screen.
Yes. Sir, next to the mic there is arrow. Unmute yourself.
Okay, so I'm unmuted and I hope you can see
Yes,
what
yes.
I'm saying.
Okay, sir. Okay.
Okay, should I stop sharing or?
Yes, it's all right, sir. We can see your PPT.
All right.
Good morning, Professor Shah. Good morning, Samrith. You there?
Good morning, Sudhir sir.
I'm a bit new to Teams, but am I right in supposing that if one is sharing the slides, then the video is automatically not visible?
Yes, sir.
Okay, all right.
If you are utilizing the same device, in that case, the same thing will happen.
So let us start, sir.
Yes, yes, yes.
Good
So,
morning, everybody. On
good
behalf
morning.
of IMS, I welcome you in 87th annual convention. Today we have a speaker, Dr. Samrith Ram from IIIT Delhi, and he will be talking on set partitions, Tableaux, and subspace profiles of regular and diagonal operators. Dr. Samrith Ram, over to you. And sir, we will give 5 minutes for questions. So try to wind up within 25 minutes so that we can have interaction if some questions are there.
All right. Thank you, Professor Neeta. I'd like to begin by thanking the organizers and also Sudhir for inviting me to give this talk. This is going to be an enumerative combinatorics talk, and the content is going to be joint work with Amrita Anshu Prasad from IMSC. So without further ado, let me begin. Okay, so the first objects of interest are set partitions. So P will denote the set of positive integers. And suppose that S is a subset of P. So a partition A of S is simply a decomposition of S into pairwise disjoint non-empty subsets. And these Y's will be called the blocks of A. So the shape of A is simply the weakly decreasing list of the sizes of its blocks. And we will write set partitions in so-called standard notation, which is to say that in each block, the elements are sorted in increasing order, and the blocks themselves are arranged in increasing order of their smallest element. So here is an example. So this set partition has blocks 1, 2, 3, 6, 7, and 4, 5, and its shape is 3, 2, 2. So it will be convenient to denote A by an array of the following form. Namely, the ith row contains cells corresponding to the corresponding block of it. So 1, 2 is the first block, and so on.
Sorry, maybe, yeah, all except the speaker can mute their audio. I think will help us listen.
Okay, so let's denote by pi s all partitions of S, and for any integer partition lambda, pi s lambda will denote all set partitions of S of shape lambda. So a tableau is simply a finite array. T is Tij, where these Tijs are positive integers, and lambda is an integer partition. So for instance, here is a tableau, and here the integer partition is 4, 3, and 2. The support of T is simply going to be all those, well, simply the entries of T, all those integers, all the Tijs. So we'll say further that a tableau is multilinear if each positive integer occurs at most once in T, and if its rows and columns are increasing. The rows increase from left to right, and the columns increase from top to bottom. So tab S is the set of multilinear tableau with support S, while tab S lambda will denote multilinear tableau with support S and a given shape lambda. Okay, so it turns out that one can associate a tableau to each set partition in a certain nice way. So let's go back to our earlier example where A is has these blocks. We can sort the columns so that they are increasing from top to bottom. Well, the first column is already in increasing order because of the way we write because the partition is in standard form. But then we sort the other columns and top justify the columns to obtain the following tableau. So by construction, the columns of this tableau are increasing, but it can be shown that the rows are also increasing. So we will call this the tableau associated to A. And the tableau associated to a set partition, this is going to be a multilinear tableau. It's also not difficult to see that given any tableau supported on S of a set partition on S of shape lambda, one can get a tableau and its shape is going to be the same as the shape of the set partition by this procedure. It's not difficult to see that it's surjective because if one given any tableau, one could simply look at the set partition whose blocks are the rows of the tableau. So this will give us a surjective function. So perhaps a natural question at this point is, so if we are given a tableau T, then we can look at all those set partitions that give you a given tableau T. So let pi T denote all those set partitions of shape lambda that give you this particular tableau, a given tableau. For instance, if we have this tableau, then one can enumerate all the set partitions corresponding to this tableau. And it turns out that in this case, there are 6 of them. Basically, the smallest elements of the set partitions will correspond to the first column of T. The second smallest elements in the blocks will correspond to the second column and so on. So one can try to enumerate the set partitions that map to a given tableau. So how many set partitions will give this a particular tableau? For that, let us define these integers Cij T. So Cij T, so we can associate them to each entry of this tableau Tij of T, except the entries of the first column. So Cij is simply the number of entries in the previous column that are less than Tij, but which occur in rows I or greater. And let Ct be the product of the Cij. So maybe here is for this given tableau, here are the values of Cij for each relevant cell. For instance, C12 is 1 because if you look at the original Tableau, we look at the element 2, and the elements in the first column that are less than 2 will contribute to C12. So among 1, 3, and 5, 1 is the only element which is less than 2. Therefore, that entry is 1. Similarly, C22 is 2 because if you look at the entry 6 in the original Tableau, then 3 and 5 are the entries in the previous column which are less than 6. So you look at all entries in the same row or greater, which are less, but in the previous column. And in this particular case, the value of CT is simply the product of these 1 into 2 into 1 into 3, which is 6. All right. If at any point there are questions, please feel free to interrupt me. I'll be happy to answer any questions. All right. So it turns out that if you are given a Tableau, then the number of set partitions, which map to T, pi T, is simply given by this number CT. So as a result, so let's denote by tab n the set of all standard Tableau with n cells. Okay, so this is all standard Young tab. Given any partition lambda of n, so set partitions of shape lambda map to Tableau of shape lambda. So if we sum up this CT over all standard Tableau of shape lambda, this simply gives us the total number of set partitions of the set of the first n positive integers which have shape lambda. Further, if we simply sum over partitions which are given length, so recall that the Stirling number of the second kind is simply the number of partitions of an n element set into m blocks. So in particular, this corresponds to a partition of n, the shape being a partition of n and having precisely m parts. Therefore, if we sum this CT over all Tableau of n cells and with m rows, then this should give us the Stirling number of the second kind. Similarly, the Bell number Bn, which denotes the set of all set partitions, you can obtain it simply by summing over all Tableau with n cells, this statistic CT. Therefore, CT is a statistic on Tableau that gives us some of these interesting combinatorial objects. So perhaps I should say here that these Bell numbers are named after E.T. Bell, but they so I guess he was interested in them in a paper subsequent to his pioneering paper in Annals titled Exponential Polynomials. But it turns out that these Bell numbers were studied even before Bell. Notably, they appear in Ramanujan's second notebook, and apparently there are some instances in medieval Japan where they were interested in enumerating these numbers for some reasons. All right, so now we can ask about Q analogs of the previous results. So these Stirling numbers and Bell numbers have well-studied Q analogs, and one can ask if those previous results carry over to these Q analogs. So suppose T is a multilinear Tableau of shape lambda. So we had this CT, which was defined as the product of these CIJTs, but now we naively replace each of these CIJs by their corresponding Q analogs. So recall that the Q analog of the integer n is simply the sum 1 plus Q so on until Q to the n minus 1. It reduces to n for Q equals 1. Therefore, this CQT is clearly a polynomial with non-negative integer coefficients And it at q equals 1, it reduces to CT. Let B lambda Q denote the sum over all tableau of shape lambda, standard tableau of shape lambda of CQ of T. So, well, CQT, when we put Q equals 0, so at Q equals 0, the Q integers reduce to 1. So CQT at Q equals 0 reduces to 1, in which case B lambda Q is simply the sum of 1 over standard tableau of shape lambda. And therefore, B lambda at 0 is simply the number of standard tableau of shape lambda with n cells. And if we put Q equals 1, then CQT simply reduces to CT. So by the previous corollary, summing CT over tableau of shape lambda simply gives us all set partitions of shape lambda. So one can ask here that, so we were able to write this polynomial as a sum over tableau. And this CQT at Q equals 1 reduces to CT, which is the total number of set partitions corresponding to this tableau T. So it seems natural to ask whether there is some statistic on set partitions that will give us these objects, CQT and B lambda. And it turns out that that is indeed the case. So to define the statistic, so let's say that a P star is all positive integers with one extra symbol infinity, which we will deem to be greater than every other element of P. So we need the notion of crossing to define interlacings. So if you are given distinct elements A, B, C, D in P star with A less than B and C less than D, then we say that the arcs A, B, and C, D are crossing if either A is less than C is less than B is less than D, or C is less than A is less than D is less than B. In other words, if we plot these points A, B, C, D on the number line and then draw an arc between A and B and another arc between C and D, so crossing corresponds to these arcs crossing as shown in the right two diagrams here. On the left, the arcs A, B, and C, D are not crossing, whereas on the right, those are crossing arcs. So let's go ahead and look at what an interlacing is. So consider this set partition is 1, 2, 9, 3, 8, and 5, 6. So an interlacing is simply a crossing of jth arcs for some j. To make this more precise, what we do is we plot all these elements on the number line first and add another point at infinity. And for each block of size k, there will be precisely k arcs. So the way those arcs are defined is that, so look at the first block of A, which is 1, 2, 9. So the 1 and 2, there is an arc. From 2 to 9, there is an arc. And the last arc comes from the last element in the block and joining that element to infinity. So 1, 2, 2, 9, and 9 infinity. And we'll draw different arcs with different colors. So similarly for the second block, the arcs would be 3, 8, and 8 infinity. Whereas for the third, they would be 5, 6, and 6 infinity. So an interlacing only comes from crossing of arcs of the same color. So for instance, here, the two orange arcs which cross, they contribute to interlacings, but the green and orange arcs crossing, that doesn't contribute to interlacings. So for instance, here, so the green arcs are the first arcs, the orange arcs are the second arcs, and the blue arcs are the third arcs. So in the example here, we actually have VAs too, because there are no crossings of green arcs, but among the second arcs, which are orange, there are exactly 2 crossings. So let's denote by VA the number of interlacings of A. So it turns out that this CQ can indeed be obtained by summing this interlacing statistic over all set partitions which correspond to this tableau T. And this is true for any multilinear tableau. So in particular, if we are looking at non-interlacing partitions of a given shape, then since these, okay, so maybe I should say here that in this equation CQT, if we put in Q equals 0, then the left-hand side reduces to 1. Recall that CQT was simply a product of Q integers. Therefore, that is 1. And on the left-hand side, this forces that there should be a single A for which Q to the VA is 1. In other words, given a tableau, there is a unique set partition which is non-interlacing and which corresponds to that tableau. As a result, non-interlacing partitions of a given shape are in bijection with standard tableau of the same shape. And if we take this a bit further, so it can be shown by, for instance, the Robinson-Shenstedt correspondence that standard tableau are in bijection with involutions in the symmetric group Sn, a tableau with n cells. Therefore, if we sum over all possible shapes, we obtain the result that non-interlacing partitions of n are in bijection with involutions in the symmetric group Sn. And since these polynomials B lambdas were defined as a sum over standard tableau of this CQT, we obtained that we could, and the fact that CQT, and from the combining the theorem and this expression for B lambda, we could write the B lambdas as the sum of a statistic of this interlacing statistic over set partitions of shape lambda. So here are some applications. So the Q analogs of the Stirling numbers, perhaps I think they go back to Karlitz. So it turns out that these numbers can be expressed in terms of these B lambdas, as well as sums over standard tableau and sums over set partitions. So the first equation is expresses the Stirling numbers in terms of these polynomials B lambda, while the second one expresses them as sum over tableau, and the third as sums over set partitions. So here in the third expression, which is the sum over set partitions, pi n m is simply all partitions of n which have n blocks, while the lambda IA correspond to the shape of A, which we defined earlier. So it turns out that this third equation, expressions of this form have already been studied. Notably, they appear in the works of Garcia and Remmel and Wachs and White in the Journal of Combinatorial Theory, and also in a more recent paper by Kai and Reedy.
Sorry, can you remind us of the definition of Q Stirling number from second kind? Okay,
so Q Stirling numbers of the second kind, they can be, so there are a few ways to define them. One, so the Stirling numbers, they satisfy ordinary Stirling numbers, they satisfy a certain recurrence. So one could use the same recurrence to give a definition for the Q Stirling numbers. The other way to do would be to think of it in terms of number of direct sum decompositions of an n-dimensional vector space over FQ into m summands, non-zero summands. That could be another way to.
M summands, subspaces.
Yeah, subspaces.
That's
yeah.
That's what I thought it may be, but just wanted to make sure. Okay.
Yeah. So it turns out that there is more than one way to define these numbers, and indeed Karlitz himself defines two variants. One is normalized variant of the other, and so on. So
I see.
yeah. All right. So nevertheless, we have these expressions for the Q-Stirling numbers, and all right. So if one computes these b lambda at -1, it turns out that this is always positive. So one could ask for a combinatorial interpretation of what that is counting. And it turns out that it's counting what are called standard shifted tableau of shape lambda. Maybe this is best explained with an example. So a standard shifted tableau is a shifted tableau basically is similar to the usual tableau, except that now the rows, each row is shifted one cell to the right with respect to the previous row. And we will say it's standard if it contains all positive integers from 1 to n for some n. Whereas we also want now the rows and columns to be increasing, but in addition, we also demand that the diagonals are increasing. That's so for instance, if we take this partition, it turns out that b lambda -1 is 4. And there are precisely 4 standard shifted tableaux of that shape. So these polynomials, so here is a small table of these polynomials. And well, the constant terms correspond to the number of standard tableau of that shape. And the sum of the coefficients is the number of set partitions. And as we have seen, the alternating sum of these coefficients, well, at least in the case where lambda has distinct parts. So perhaps I should have emphasized this a bit more. So the parts of lambda need not necessarily be distinct. The largest part alone could have a multiplicity greater than 1. So for those partitions, b lambda at -1 equals the number of standard shifted tableaux.
Excuse me, sir. We have 5 minutes left, please.
Okay, all right. Thank you. I'll keep that in mind. All right. So these were 3 evaluations. So b lambda at 0, 1, and -1, they count these interesting combinatorial objects. One can also look at a 4th interesting object, that is that these b lambdas can be used to count. And for that, we will need to define subspace profiles. So let FQ be a finite field with Q elements. And suppose that delta is a linear operator on FQ to the n. A subspace W of FQn, we'll say that it has partial profile mu if the dimension of W plus delta W so on up to delta to the j minus 1 W equals the sum of mu1 up to mu j for each j going from 1 to k. In particular, if that direct sum stabilizes at the kth stage, then we will say that W has delta profile mu. So for instance, if you take an m-dimensional delta invariant subspace, then that has profile m. Whereas a subspace that is spanned by a cyclic vector for delta has profile simply a partition where all parts are equal to 1. The partition of n with all parts equal to 1. It's not difficult to show that these mu j's should be weakly decreasing, and therefore mu is a partition of some integer not exceeding n. So one can show that, so if we denote by sigma and mu the number of subspaces with a given delta profile, then this sigma and mu is a polynomial in Q that depends only on the similarity class type of delta. So this notion of similarity class type goes back to the work of Green on the irreducible characters of the finite general linear groups. Maybe in the interest of time, I will leave that undefined and come back to it a bit later. The similarity class type, it simply depends on the degrees of the irreducible polynomials in the conjugacy class data and the partition and the integer partitions that occur there. So it turns out then that when this delta is a regular split semi-simple operator, then the number of subspaces with a given delta profile mu is can be written as up to a factor of powers of q and q minus 1 and a constant factor. These b lambda q, these polynomials come in again, and here mu prime is the conjugate partition to mu. As a corollary of this, what one can do is look at all m-dimensional subspaces which are counted by the Gaussian binomial coefficient and choose mq on the left. And one could look at subspaces and sum over profiles, the number of subspaces of a given profile. And that yields this identity, which again goes back to Karlitz. This identity can also be used to express the Q Stirling numbers in terms of the Gaussian binomial coefficients. All right, I guess I'm more or less out of time here. Maybe there isn't time for splitting subspaces. So maybe I'll stop here at this stage.
Thank you, Professor Smith. Any question from the one question we can entertain? Professor Sudhir, do you have any question?
Yeah, actually, can you very quickly show what you had to say about splitting subspace?
Yeah.
Okay, so this is pretty much what I had to say. So I wanted to say that the number of splitting subspaces, determining that is an open problem. And yeah.
You're able to solve this general problem?
Not the general one. We know that the general answer is a polynomial in Q, but in the case of regular split semi-simple, one can get the number of delta splitting subspaces of a given. And this also corresponds in the case equals 2 with what were called chord diagrams, which were studied by Tushar.
Okay.
There's another interesting open problem there, stamp folding.
So the case in the classical splitting subspace conjecture as a special case, with multiplication by a primitive element.
Sorry, I think I missed what you said.
No, I said the set of operators for which you're able to solve that problem
Right.
includes as a special case multiplication by a primitive element that.
Oh, I see. So that multiplication by primitive element, that's actually a different case that corresponds to the irreducible characteristic polynomial. And that's a different case. Yeah. This problem is still open in general. So there are some special cases, basically the nilpotent and the Chen and Seng case, and this regular split semi-simple, and a few other cases where some minor assumptions on the degrees of the polynomials in the conjugacy class data, if you assume, one can prove it. But in general, it still remains open. Yeah.
Thank you.
Thank you, Professor Smith and Sudhir sir and other delegates. Because of lack of time, because I am getting a notification that I'm 1 minute only left with. Thank you on behalf of IMS for accepting invitation to deliver an interesting talk. Thank you, everybody.
Thank you, Dr. Samrith, IIIT Delhi for wonderful talk. And I'm also thankful on behalf of MGM University and IMS, Professor Neeta Shah, Gujarat University, Ahmedabad, for chairing this session. So thank you, everybody, participants and all the dignitaries. Thank you very much.
Have a good day.
Thank you. Thank you.
Very nice talk.
Thanks. Thank you.
You can share the slides, something.
The slide is it? Just a second.
Yeah, you can just no, just email to me.
Okay, sure.